All right, so what are we able to do with ethers? Now, to a large extent, the answer is not much. In general, ethers are not very reactive, and because of that, they require very harsh conditions in order to react, with the exception of a few special circumstances that we'll talk about here. But for most ethers, getting them to react requires very harsh conditions. Now, under the right conditions, you can essentially cleave an ether, do the reverse of the Williamson ether synthesis. In order to do that, you take your ether and you add a strong acid such as HBr to it in water and heat it to boiling. Now, these are generally very harsh conditions, especially in the presence of such a strong acid. But assuming that your ether is able to survive, in 2 steps, we'll go from the ether to an alcohol plus an alkyl halide. How does that happen? Well, again, with a strong enough acid, the lone pair on oxygen will attack the hydrogen from HBr, giving us a protonated oxygen here. And if you recall from when we were talking about, SN1 and SN2 reactions, one of the reasons that we do this is to make the oxygen into a better leaving group. O- on its own is a pretty bad leaving group, but once we protonate it, get OH+, now we have a very good leaving group. Our nucleophile is the Br-. And where is it going to attack? Well, it can, in theory, attack on either side of the oxygen. But this is, again, an SN2 reaction. And so it's going to attack the side of the ether that's less sterically hindered. In this case, we have the primary side versus the aromatic side of the ether. The primary side is significantly less substituted, and so our nucleophilic attack happens that way. We kick out the alcohol and get our products. And again, this is one of those reactions that is used in some very specific situations, but generally isn't that useful because the conditions are so harsh. So the main place where reactions of ethers is useful is when we're dealing with epoxides. So epoxides, recall, are these 3-membered rings containing oxygen. And we learned in Organic 1 how we make these. We make these through the reaction of an alkene and MCPBA. Now, it turns out when you add a nucleophile to an epoxide, that nucleophile can force the epoxide to open, which forms this new carbon nucleophile bond, and then after protonation gives you an alcohol. Now, why is this all of a sudden okay? We've said on a number of occasions, especially in the SN1, SN2 chapter, that O- is a bad leaving group. So is O- still a bad leaving group, or why is it okay all of a sudden in this reaction? Well, it's not that O- all of a sudden became a better leaving group. It's still a bad leaving group. But when this step occurs, we release all the ring strain from the 3-membered ring. And it's basically a case of what's worse. Is it worse to have the O- as a leaving group, or is it worse to have the 3-membered ring? It turns out having the 3-membered ring is worse, and so given the opportunity, The molecule would rather have the bad leaving group than be strained like this. Now, these type of reactions can be done both under acidic as well as basic conditions. And it actually makes a difference which set of conditions you use. Now, in the example here, it wouldn't have mattered because the epoxide was symmetric. But if we have an epoxide that's not symmetric, which could be something as simple as this one, at this point, it matters whether we use acidic or basic conditions. If we use acidic conditions, then our nucleophile will come from the more substituted carbon. But if we use basic conditions, then the nucleophile will come on the less substituted side. So we actually have complete control over where the nucleophile is going to go based on the reaction conditions. So how do we do that? And why? So under acidic conditions, the first step, very much like the previous reaction, is that the lone pair on oxygen will attack the acid, which protonates it again to make a better leaving group. Now, even though the formal positive charge is on oxygen, knowing that oxygen is more electronegative than carbon, that oxygen is pulling electron density away from the carbons it's bonded to. We also know that the more substituted a carbon is, the better able it is to donate, the better it can support positive charge. So our more substituted carbon here is going to be more delta plus, and therefore it's going to be a better electrophile. And so now if we add a nucleophile, for example water, it'll add at the more substituted carbon and open the epoxide up in that way. After loss of the proton, we get our product. So that's under acidic conditions. What about under basic conditions? So we could say that the acidic conditions are the reaction is SN1 like. Basic conditions are going to be more SN2 like. So under basic conditions, there's no protonation of the epoxide, so there's no cation formed. So where will our nucleophile attack? Our nucleophile, as in an SN2 reaction, will attack where there's more space. That's at our less substituted carbon here, and then after protonation, we get our product. So ring opening of an epoxide is the one major exception to how epoxides can to ethers reacting, and we have complete control over which carbon it attacks at based on acidic versus basic conditions. Right, so there's not really much else in terms of reactions of ethers, but there is another significant role that ethers can play, and that involves a class of molecules known as crown ethers. Crown ethers were responsible for the 1987 Nobel Prize in Chemistry. And crown ethers have a basic pattern. That basic pattern is they have some number of oxygens, and some number of carbons. And they're in a large ring in some sort of repetitive pattern. And so, one like the one I've drawn here, we would name this compound 15 crown 5. The 5, the number on the right, is the number of oxygens, and the 15 is the total ring size. So, what's important about crown ethers? Well, crown ethers are a good example of what we call a phase transfer catalyst. All right, what do we mean by that? Well, previously we've learned that a compound like potassium permanganate is a very effective oxidant for organic compounds. But let's say that the compound we need to oxidize is relatively nonpolar, and we need to get potassium permanganate into a nonpolar solvent like benzene. Well, potassium permanganate, being an ionic compound, is pretty much completely insoluble in benzene, and so it doesn't work. But all of a sudden, to this mixture, we add 18 crown 6. So 18 crown 6 now is a 18-membered ring with 6 oxygens. So looking something like that. Well, in the presence of 18 crown 6, the potassium cation from potassium permanganate can go into the middle of this crown ether, and it's essentially shielded or blocked or hidden by the nonpolar crown ether. And so this nonpolar crown ether is able to dissolve in the nonpolar solvent. It brings the potassium ion along, which normally wouldn't be soluble because the crown ether hides it from the solvent. And then the permanganate ion is able to come along to balance charge. And so by using this type of compound, we can get an oxidation using this very polar oxidant to take place in a completely nonpolar solution.